Hello, everyone. Welcome back. Today, I want to talk about optimization problems. What it means to optimize something. So our goals, and as it says, to be able to find the absolute minimum maximum values of a function. That will be important in doing this, and then be able to solve optimization problems using derivatives. We may have solved some of these, especially involving quadratic functions in algebra, but this is how we can do this using calculus. So in general, optimization, what that is, to optimize something means we want to find the largest and smallest values. So many areas from science to business, we want to find values that give us the maximum or minimum outcomes. So for example, when you're in your job, you want to maximize the amount of money you make, or you want to, and also maybe you want to minimize the amount of time it takes to drive to work, for example. Or for business, you want to maximize profit and minimize cost or minimize loss. Or in science, you want to engineering, you want to maximize performance, may minimize friction, things like that. So a lot of things you want to times you want to find the largest and smallest values of something. And when we can express some of these things in terms of functions, in terms of formulas, then we can often find a maximum or minimum value. So look at a few problems. Here's a guide. I took from a textbook, but it's a pretty good idea of how to approach kind of problem solving in general, especially these optimization problems. As usual, read the problem carefully. Make sure to identify the variables and organize given information in a picture or some way like that if you can. That would be helpful. It says identify the objective function, the function being optimized, right, in terms of the variables of the problem. So basically, you have some quantity you're trying to optimize, whether to find the minimum value or the maximum value. You want to determine what that is, and often that may have more than one variable involved. So the next part is something called identify the constraint or constraints. Basically, these are other equations that other ways we can relationships between the other equations. My goal, and at least in this optimization, what we're looking at here is to get down to one equation, one variable. That's something we know how to optimize. We can find the derivative of that equation, just one equation with one variable. So basically, we want to take the problems we have here and then try to turn them into an equation with just one variable. And that's what you see in this video. Now, some problems in real life, you can't do that to turn this to one variable. They may have more variables. And there are types of calculus that will deal with that called multivariable calculus, but we're not doing that today. So once you get your function you're trying to maximize or minimize your constraints, you basically may turn this function into, it says write the objective function expressed in terms of a single variable. Basically, want to find the value of interest, and then we'll use calculus, maybe use a first or second derivative test, other methods of calculus, and to find out what the maximum minimum values are. And also at the very end, I just put down a reminder of how to find the absolute maximum minimums on closed intervals. Sometimes we'll have a closed interval, sometimes not. This is how you do it. So of course you find your critical values on the function. You also evaluate the function at the critical points and the endpoints, and you find the maximum and the minimum values of those as you need to. So that's just a reminder in cases where you need to do that. So let's go here to the right and look at our first example. So this one says, find the numbers x and y satisfying the equation 3x plus y equals 12, such that the product of x and y is as large as possible. Okay, so the product of x and y, remember product means multiplication, so let's call that p, and that's going to be just x times y. So we're trying to find and maximize this, but once again, we have two variables. That's the problem. What we want to do then, first of all, we want to maximize p equals x times y, okay? We need to get this, we want only one variable, okay? We're going to do then, we're going to use what's called our constraint equation or constraint. And we're given this other equation. Now, if you remember in general, if you have however many unknowns or variables you have, you usually need that many equations to solve it. Essentially, that's what we're doing. We use our constraint equation, 3x plus y equals 12. And let's just solve this for y. That's the easiest thing to do. We do that, then we have y is equal to 12 minus 3x. Just subtract 3x on both sides. Now, we're going to substitute this into our equation for p, and that's going to give us then p, and this is now a function of x. P is equal to x times y, and y is 12 minus 3x. And if you just multiply that out, that's just distributed. It's going to be 12x minus 3x squared. Okay, so this is our function that gives us, basically, if you plug in an x, this will give us the value of the product of x times y based on this constraint, as long as this is true. Okay, now a couple things I want to mention is think about what our possible limits are for x and y. Okay, now obviously they both have to be bigger than 0. All right, so obviously, let's call them our bounds. Okay, so x has got to be greater than 0. What about y? Well, for y, basically this, which is y is 12 minus 3x, that's also has to be greater than 0. Okay, so we actually just solve this inequality. So we have negative 3x is greater than negative 12, and then x is less than 4. So those are our bounds. X has got to be greater than 0 and less than 4. So we have to look for values within that range. Okay. Now, technically, I guess you could think of this as being less than or equal to. You could also do that. It makes it kind of a closed interval. But you don't have to. But obviously, x is, if either one is 0, that makes the whole thing 0. So it's not likely that would be a maximum value. Okay. All right. So let me say next, let's find the derivatives, p prime of x and p double prime of x. Okay. So p prime of x, the first derivative from here, that's going to be 12 minus 6x. Okay. And then p prime, double prime of x, is going to be just negative 6. Okay. So now, next, let's find our critical values. And actually, I realize I need to move some of this stuff down. Okay, hang on a second. Give me a second here. Go ahead and get a whole new page. Let me just delete this. So give me just a moment to sort this out. I thought I had enough room there for this problem, but I didn't. Okay, let's go back up here. Now I have more than enough room. Okay, so let's just write that again. So first derivative p prime of x is going to be, what I said, 12 minus 6x. And then p double prime of x, the second derivative, just negative 6. Okay. Now, so let's kind of go through the process. So we want to find out, let's find our critical values. Okay, so take our first derivative set equal to 0. 12 minus 6x is equal to 0. So negative 6x is equal to negative 12. X is equal to 2. Okay, in this case, only one critical value, 2. Okay, so we want to have a Hoeffler maximum minimum. That's where it's going to be. Now, let's actually use the second derivative test to tell whether or not this is a maximum or minimum. Okay, so remember what we're going to do then is we're going to plug this into the second derivative and find out what the sign is. So f double prime of 2, actually remember f double prime is just -6. It's always -6 as a constant. This is -6, which of course is less than 0. This tells us, so basically, the function there is basically going to be concave down, opens down. And what that tells us then, so x equals 2, not x equals 2 is a maximum, but basically that we have a local maximum at x equals 2. So we have a local maximum at x equals 2. Okay, now let's actually go back to our problem just a second. So what did it ask? We wanted to find the numbers x and y, which gives us the maximum product. Okay, so that's x. Now find y. I'll just say then for y, we had a formula for y from our constraint equation. And y was 12 minus 3x. Let's find out what y is. So y equals 12 minus 3x, and x is 2. And that's going to be just 12 minus 6 is going to be 6, okay? So, and then one more thing. If x equals 0 or x equals 4, then our p of x is going to be 0. That's what we said a minute ago. Okay, we found our bounds. Basically, if x is equal to, because if x is 0, then there's no, basically our whole thing is 0, be 0 times something is 0. And if x is 4, this becomes 0, y becomes 0. So basically, our maximum is right there. So maximum product is, or x equals 2, y equals 6, and then p so our max product is 2 times 6, which is equal to 12. Okay. Now, also one thing, we can also see this if we actually graph this using Desmos or anything else. Let's graph this really quickly. So our function was y equals 12x minus 3x squared. And if we take a look right here, so our bounds where this is positive, because we're talking about our bounds then are going to be at 0 and 4, as we said, and then our maximum is when x is 2, and that's the maximum value then is 12. Okay, let's look at our second example. Okay, hang on just a second. Okay, yeah. So number 2 is our second one. I probably also need some more space here as well. So let's get some more space. Okay. Now this problem actually has to do with volumes. It says, suppose an airline policy states that all baggage must be box shaped with the sum of the length, width, and height not exceeding 108 centimeters. What are the dimensions of volume of a square box base with the greatest volume under these conditions? So we have a square box, okay? Let's imagine kind of what that looks like. So basically trying to draw a box. Okay. Now, think about a box. Normally, it's kind of what's called length times width times height. Okay, those are the dimensions of a box. All right. Now here it says a square-based box. So actually, let's call so our box is a square. Let's call both those sides x and x. Okay, length and width are both x. Then our height is going to be y. Okay, so there's our box. Now, it also says we have a constraint. This is kind of a made-up constraint, but the constraint says the sum of the length, width, and height not exceed 108 inches. Once again, these are also all in inches. It's important when you have units, make sure you use the correct units and use them, get the correct final unit. Okay, so our constraint says that basically x plus y has to equal 108. Okay, the sum of the length, width, and height. Sum means remember to add. And here, so we have two x's. Let's write this as 2x plus y is equal to 108. Okay, what we're going to do then is want to maximize the volume. Okay, now, so the volume of a box like this, any kind of box, is going to be length times width times height. Okay, and so in this case, that's just going to be x squared times y, because it's length times width times height. All right, now once again, like our previous example, we have something now with two variables. We need to get this down to one variable. Okay, so I want to write y in terms of x using our constraint. Equation. What that means is I'm just going to solve this equation for y, and that's easy to do. Subtract 2x on both sides. So that's going to give me then y is equal to 108 minus 2y. Okay, so now what we have now is the volume. I'm going to call it v, which is now be a function of x, is going to be x squared times 108 minus, I'm sorry, not 2y. 108 minus 2x. Okay, and now we have the volume as a function of just x. Now, let's think about our bounds on this. Okay, so kind of like in our last example as well, x has got to be greater than equal to 0, or mostly just equal or greater than 0. Okay, because actually if it is 0, there's no box, but you get the idea. So actually, technically, you probably just say greater than, just simply greater than 0. So unlike the last example, we're just dealing with numbers, now we're dealing with the box. If x is 0, there's obviously no box. Okay, now what about y? The bounds on y. Well, y is this. So for y, which is 108 minus 2x, has got to be also greater than 0. And so we solve this inequality. We have minus 2x is greater than negative 108. And so x is going to be less than 54. Okay, so those are our bounds. So x can range anywhere from 0 to 54, but not actually including those. If it does include those, then we actually have no box. Okay, now this is going to follow kind of the same pattern as the last one. So now that we have our function, and also one more thing, I'm going to distribute this. So 108x squared minus 2x cubed. Let's find the derivatives. Okay, so v prime of x, first derivative, is going to be 2 times 108, which would be 216x, minus, and the derivative of negative 2x cubed is going to be negative 6x squared. And then the second derivative is going to be 216 minus 12x. Okay. Now, let's find our critical values, value or values. The last one just had 1. We could have more than 1 this time. All right, so we know how to find critical values. So set this equal to 0 and solve. So 216x minus x squared is equal to 0. And now the best thing to do here is minus 6x. Is factor this out, and that does factor. We can take a 6x out, and what we're left with is In a second. Of course, you can try this on your calculator. 36. So 36 minus x. Okay, and so if you remember this, how to solve this, and so set each one equal to 0, so have 6x is 0, and then 36 minus x is equal to 0. So here are possibilities where x is 0, and then x is equal to 36. Okay, now, obviously we said a minute ago that x, so this one is not possible in terms of not possible for our application. Okay, as far as a function, as far as just working with numbers, that's fine. That would be a critical value, but since x is supposed to be a dimension, it can't be 0, so this is not possible. This time, since we only have one critical value we can actually work with. Makes sense. Okay, so I think I can squeeze this in over here. Let's do our second derivative test over here, and it's probably easier to do this one. Okay, so remember the second derivative test, we're going to plug in our critical value into our second derivative, and probably need our calculator for this. And so it's going to be 216 minus 12 times 36. Over here, we're mainly interested in the sign, which is going to tell us whether or not we have a local maximum or local minimum here. Okay, so and so that's actually going to be negative 216, of course, which is less than 0. It's negative. So what that tells us then, it's negative. That tells us that basically this function is here is concave down, and also implies that we have a local maximum at x equals 36. Okay. Now, one more thing, we can think of these, we said before that our bounds were basically 0 and 54. It couldn't really include those. Okay. And so basically this is our only critical value. So in this case, think about terms of finding absolute value. Also, I'll say since if you plugged in that, you get 0 for both of those. Since x, you plugged in these values, 54 to our function, 54 or x0, you get 0 for this thing. I'll also say since v of 0 equals v of 54, which aren't really bounds since they aren't really included, but still they'd both be 0. So our absolute maximum is at x equals 36. Okay. I also remember that's also 36 inches. It's about our units. It's 36 inches. All right. Now let's look back at our problem. Make sure you understand what it was defined to solve. What are the dimensions and the volume of this square? So we want to find not only the volume, but also the dimensions, the volume. Okay. So that's x. Y, then let's plug that in. 108 minus 2x. So 108 minus 2x, 2 times 36. And that turns out to also be 36 inches. Interesting. Okay. And so, finally, what's our volume? Is going to be, it says it's going to be x squared times y, going to be 36 inches squared times 36 inches, or 36 cubed. And that's going to be 46,656 inches. Now, think about our units here. We're squaring inches multiplied by inches again. That's inches cubed, and that volume is always units of length cubed. So that's our maximum volume. So the x and y values give us our maximum are here at when x and y are both 36 inches, and the maximum volume is this. Now, let's take a look at this quickly on Desmos. And this is the only bad thing about doing this on Desmos is this particular one is going to be kind of hard to see. So let's actually, where our function was, y equals 108 x squared minus 2x cubed. And this one, unfortunately, is just really kind of spread out. But you notice right here, we say go from 54. That's one of our limits, and also 0. What we're going to do is we're actually going to go to make an adjustment here. All right, so we can adjust our x and y axes. So x, let's put x, let's say make it go from 0 to 60. So we can actually see the 54. Okay, and now y, let's make it go from 0. And remember, our maximum volume is quite high, so let's make it 50,000. Okay, and that gives us a better view anyway, what we're looking at. All right, so here, as you can see our graph, okay, that was actually a local minimum there at 0, but since that's the boundary there, we can't go any further, but that would also be a local minimum. Remember, we'll go between 0 and 54, and right here, a local maximum at 36, as we said, our maximum volume is 46,656 cubic inches. Good. So we got what we expect. Okay, and then one last problem. And very similar to the last one in a lot of ways. So their volume problem. This time I actually do give us a picture to look at with. So let's see what this one says. It's going to work basically the same way. All right. So basically, 2 squares of length x are cut out of it. So basically, starting out with this piece of cardboard, which is going to be 18 inches by 18 inches, 18 inches long, 18 inches wide. Okay. Now we're going to cut out pieces of size x right here from it. Okay, right here and here. Okay. And then also we can cut out these lengths right here, length of 9 right here, 9 inches by x inches. So piece of cardboard of 2 rectangles of length 9 and width x are cut out the corners. Those 2 corners are cardboard, as we see. So we're cutting those out. Those darken onto what we're cutting out. We're going to make a box with a top here. So here's our base. Here are our sides, and there's a top that's going to fold over and get this completed box. Now, so basically, we want to find the dimensions and the volume that gives the largest box we can be formed in this way. So it's very much like the last problem. Same idea. Okay, let's think a bit about what our length, width, and height are going to be. So think about when we fold this box up, our height is going to be x. Okay, these are all in inches. I'll just use the box here, the picture to give us to help us out. Okay. Now, let's think about this length right here, this length. So it's going to be here. So basically, this starts out with 18 inches long, and we're cutting a length of x out of each end. So this length is going to be 18 minus 2x along here. Then our width right here, this dimension, think about how we're going to get that. Maybe easier to see it from here. So here we're cutting out from here to here is 9, and so it is here as well. This is also 9 inches total. We're cutting out x there. So what leaves us with is going to be 9 minus x inches. Okay, so that's our length, width, and height. Now, of course, the volume of a box like this is equal to length times width times height. And then that's going to be, if we put all this together, x times 9 minus x times 18 minus 2x, all in terms of x. Length times width times height. Okay, I want to maximize this. I want to find the x that maximizes it. Okay, now in a similar way, think about our bounds. What can x be? Okay, so obviously x has got to be technically greater than 0 by going and put it greater than or equal to 0. If you think about this, what will make this part of it, and that's our width, what's going to make that 0? It's going to be if it's 9 or greater. Okay, if x is bigger than 9, it's make that negative, and the length can't be negative. Okay. And actually the same thing here. If x is also 9 here, or greater than 9, it's going to make this one negative. So basically x has got to be between 0 and 9. And we'll see that when we graph it. Okay. Now I want to maximize that. And so this is going to be, in fact, let's just call this now. This is our function volume x. So let's find our derivatives. Now, actually, I'm going to start out with, and I'm not going to show this, I'm not going to show these details here, but what you want to do, the best thing to do is probably just to multiply all this out. Now, you don't have to. You could use a version of the product rule. You're going to have to multiply things out anyway. So if you do this, let's write this as Vx. And I've already done that for you. This is something you can try on your own to make sure you get the same thing. You should get 6x oh, look at the wrong thing. No, hang on. So if we multiply that all out, we should get 2x cubed minus 36x squared plus 162. Okay, so that is our function for our volume. Let's go with x moving between 0 and 9. Okay, now let's find our derivative. So first derivative, just go down the line. So derivative of this is going to be 6x squared. Okay, minus 72x plus 162. That's first derivative v prime, and then v double prime is then going to be 12x minus 72. Okay. Then, once again, you want to find our critical values. Okay, it's going to set this equal to 0 and solve. So 6x squared minus 72x plus 162 is 0. And fortunately, this will factor. I'm going to show you the factored form. So you can take the 6 out and then also factor the rest of it. And that's going to factor into basically 6 times x minus 3 times x minus 9. And so if we set each one equal to 0, let's get our critical values. And I'm kind of moving through a couple steps here at once. You set each one of these equal to 0. And so you have x equals 3 for our critical values and x equals 9. Okay. But as we said a minute ago, actually 9, we can't really use 9 as a possible maximum minimum value. Okay. So this one is not not allowed for application as far as just it is a critical value of this function, but for application, we can't use that. So actually I have only one critical value. Okay. So once again, let's do the second derivative test. And let's find out what we can about this. So we're going to plug this value, our other critical value, into the second derivative. Okay. So v double prime of 3 and find out about its concavity. So 12 times 3. So 12x minus 72, 12 times 3 minus 72. And that is going to be, it's going to be negative 12. This is going to be 36 minus 72 is negative 36, which of course is less than 0. That tells us here the function is concave or up or opens, sorry, concave down or opens down. Okay. It also tells us we have a local maximum value at x equals 3. Okay. Now, one more thing. So that's where our local maximum is going to be. Now, let's also think about our other, think about this much like find the absolute extreme values. Okay. So these are also bounds. And once again, technically, either one could actually be equal to 0 or 9. But if we just think about that, so basically, if you plug both those in, your volume is going to be 0. I'll just say, and V of 0 is equal to V of 9, which is equal to 0. So we have an absolute maximum at x equals 3. And once again, this is 3 inches. Okay. Now let's find our other length and width. Okay. So this is the height is equal to 3 inches. Okay. And the width, what I call the width, I think doesn't really matter, but I think I call it 9. Yeah, 9 minus x, what I was calling the width. So 9 minus 3 is equal to 6 inches. And then what I call the length was 18 minus 2x, or 18 times 2 times 3. That'd be 18 minus 6, which is going to be 12 inches. Okay. And then, finally, the maximum volume for those constraints, for the box made like that, is going to be equal to, of course, 3 inches times 6 inches times 12 inches. 3 times 6 is 9, times 12 is 108. And once again, this is also inches cubed. So we have inches times inches times inches. That's inches cubed. And volume is always in units of length cubed. Okay. Last thing, then, let's actually check this with Desmos, make sure we get the same thing. Turn this one off. We'll also have to change our scale. Let's just go ahead and graph it first. So y equals 2x cubed minus 36x squared plus 162x. And yeah, so we have to change our scale around because we can, I can't really see anything here. But remember, we said this has to go between 0 and 9. So John's going to adjust this. So x, let's make it between 0 and 9. And our height, let's make it between 0 and, so our maximum should be about 108. Let's make it 120. Okay. Oops. And 216. Hang on a minute. So the 3 is right, the 216, which I must have calculated something wrong. Let me take a quick look. So it should be 216, not that. Oh, yeah, duh. Okay. Sorry about that. I added 3 and 6 instead of 3 times 6. So that should be 3 times 6. So do the recalculator, show the calculator anyway. 3 times 6 times 12 is 216. Sorry about that. Yeah, but it's a good thing always to check graphing it and make sure we get that right. There we go. Let's take one more look at the graph. Yeah, that's exactly it. So once again, this goes between 0 and 9. And all we can see, we have a local minimum at 9, but we couldn't include that. Then our maximum with x is 3, and the maximum volume is 216. Okay, so today what we learned was kind of review. We learned how to actually use calculus and help us optimize something. So we're going to optimize going to be finding maximums or minimums. The ones we look at it here, we just involve maximums. Finding minimums the same way. Okay, so basically you'll set up your problem, figure out the function it is you need to optimize, find the maximum of. Basically, you need to use some kind of constraint equation to get that into one equation with one variable, and then use calculus. Find the derivatives, use the derivative test, find your critical values, and find which critical values or possibly endpoints are going to give you the maximum or minimum value you're looking for. Thank you. Have a good day.